right. Without further ado, it's a pleasure to have Professor Ramya Vinayak from Wisconsin, and she's going to tell us about some very interesting work. I think appeared in IKEA.
Yes. Yeah.
Okay.
Yeah.
Thanks.
Yeah. Thanks, Sujay. Yeah, thank you, everyone. It's a pleasure to be here. It's been a while. Like, I think the last time I visited Austin was when I was a graduate student, like, almost 10 years ago. So really nice to be here. Today I will be talking about modeling and learning personalizable reward models with the motivation of being able to be helpful in pluralistic alignment. Yes, I need to. Okay. So I start with some motivation and like talk about the reward modeling framework, some results on how many samples would you need to be able to learn these personalizable rewards. And in the end, I'll show some of real data experiments that, to highlight how some of these modeling frameworks work pretty well in practice on real scenarios. But before I jump into the talk for today, I also want to highlight a couple of other topics that might be of interest for the audience, but that's not the part of this talk. So it's like, but if you want to talk about these, offline, I'm very happy to chat about these as well. Another like thread of work in my lab focuses on how do we create statistically meaningful, reliable systems that utilize black box ML or AI models, or sometimes even white box ML or AI models, but they are models that are very difficult for us to mathematically understand, how they are working, but we want to augment them with frameworks that will allow us to give reliability guarantees. An example is how do we create reliable data sets with human AI collaborating together in these systems called auto-labeling. In this setup, usually like what you have is you have a set of unlabeled data and some error tolerance that you're willing to accept with some high probability. The goal of this system is to output a labeled data where a part of it is going to be human labeled and the rest of it is somehow automatically labeled, with the guarantee that among the automatically labeled data, no more than epsilon fraction are in error. Now, how and why should such systems work? How much data would you need, and how we'll learn some of the key components of these systems. So those are the questions, some of the questions we also addressed in our works. And also like the other places where you do need reliability guarantees in safety critical applications, for example, healthcare. And there's a lot of very interesting tools and techniques in ML and AI that have been developed. For example, OOD detection, right? You have an ML model that's been trained really well on some training data and validated really well. But when you deploy it, it can see data that might not necessarily come from the same distribution. So there has been several works that propose techniques to, when you have a new point, use some kind of scoring function to decide whether it is in or out of distribution. However, many of these methods, while they seem to work well on data, certain benchmark data sets, they're often not equipped with the kind of statistical guarantees. Like, for example, in systems like this, you would want to have like a control on FPR. For example, if you're deploying such a system over time, you want to guarantee that no more than 5% of out of distribution data would ever be classified as in distribution data. So how do we kind of provide these guarantees? So many of these systems kind of have this human in the loop or human AI collaboration setups where you can actually provide statistically meaningful guarantees even while working with ML models that we don't quite know how well, in theory, how they're working. Right? So now I want to get back to the topic of today's talk, where we will be looking at how do we learn personalizable reward models. And the bulk of the talk will focus on the first 3 papers listed here. And I will not have the time to talk about the last one, where we were focused more on learning a prior over user preferences rather than actually being able to do personalized, like necessarily recommendations themselves. but it's more of a statistical question there. Happy to chat about it offline. Okay, so why do we care about personalized reward models? So as most of you know, the modern very large models, whether it is like image generation models like diffusion models or like language models, these generative models are trained on internet scale data, but they're not immediately deployed, right? They undergo a lot of fine tuning. And one of the fine tuning is called alignment with human feedback, right? So what's done here is, let's say, take the example of like an image generation system. You have a prompt, say image of a cat, and the model like outputs like an image of a cat. But we want to make sure that these output images are more aligned to human preferences. So the way this kind of alignment is done is you have a bunch of prompts. For each prompt, you output two outputs, show it to humans and ask them like, which of these two outputs would you prefer? And you collect lots and lots of such pairwise comparison data. And then you want to use that data in order to make the model better in terms of essentially outputting generations that are more preferred by humans, right? So at a high level, most of these systems kind of either explicitly or implicitly end up learning like a reward function, which takes in both the prompt and the output of the model as input and produces some score to it. And the goal is that you want to learn a reward function that outputs like better score when the output for a given prompt is more preferred compared to other outputs, right? And how this reward function can be used works very, in different ways. There are methods that fine tune the model itself, but more and more there is also a lot of interest in inference time methods where instead of actually fine tuning the whole model, you use the learned reward function to reshape the final scores and probabilities to kind of adjust what you finally output, right? So in this talk, I'll be focused mostly on the how do we learn these reward functions, in particular, how do we learn personalizable reward functions. Like the main focus of personalized reward function is motivated by this aspect of when we are trying to align these AI and ML models to human preferences and values, it's natural to ask ourselves like whose preferences and values are we aligning them to? Because not everyone has the same preference and same values, right? And this is something that was also identified in the NLP community. And so this is a position paper that appeared in ICML in 2024. They were highlighting the issues with the then existing modeling and learning frameworks in RLHF that were primarily focused on homogenized assumption. And so the question that we were interested in at that time is to see, okay, how do we even model diverse preferences? When would such models be learnable? How much data would we need per person to be able to learn such models and so on? And while I'm motivating most of this using AI alignment setup, everything that I will talk about today would also apply to the classical questions related to recommendation systems that have been studied in the literature over the last few decades, but also a lot of interesting questions in behavioral and cognitive psychology, where the interest is in really understanding how humans make preferences when they're given alternates. Also in survey and social sciences, when you're trying to kind of elicit and learn opinions and preferences of people. So a wide range of applications beyond alignment also benefit from these kind of like learning good reward models. Now, let's take a look at like what was the underlying modeling assumptions that were used in the series of works on in the beginning for RLHF, right? If you go back and look at the OpenAI's like RLHF paper or like the series of papers that came later, mainly what they rely on is Bradley-Terry model, right? So you have some prompt or context that inputs is input into the model. So that's denoted here by XC. There are two alternates, XL and XR. The probability that the alternate XL is preferred over XR is given by this kind of a ratio of these exponentiated rewards. Essentially, what this is saying is that it's like a sigmoid of the difference of the rewards for the two alternates for this given prompt. Right? So if we peek into Bradley-Terry model details, like what does Bradley-Terry model assume? So Bradley-Terry model assumes that given a bunch of alternates, that there is a true underlying score associated with each of the alternates. And if I knew them, I could arrange them to have a ranking of these items. And when I pick two pairs and query them, I'll get an answer of which one is preferred with some noise. And that noise is modeled as this ratio of like the true weights or scores, right? So, usually this ends up, the weights are, non-negative. So that's usually also parameterized using exponentials. That's where you get the e to the power r's. So at the core, it assumes a single ordering of the alternates being compared. So inherently, by using the Bradley-Terry model, we are assuming kind of a homogeneity in preferences across the population. So when there is a pair being compared, and I give a different answer than say Sujay or Amy, it's like kind of can get like a very different flavors that people can get from actually the underlying preferences themselves being different than saying that, oh, it's the same preference that Sujay and I have, but there is some noise when the queries are made. And so that's what we want to kind of get over and say, no, we want to be able to learn different preferences for different people. But the other thing that I would like to highlight, but might not necessarily be as limiting as the homogeneous assumption, but it is something that we should also pay attention to when we are modeling is like how much do we need to assume about different parts of the model. So Bradley-Terry model very specifically assumes sigmoid function for the noise. But actually, to be able to learn from pairwise comparisons, we don't necessarily need to assume a parametric form for these noise models. And I will comment on that later, because that could also limit ourselves when we make these modeling choices so strictly. It also limits ourselves to what if there is a model mismatch in terms of the noise, right? So around the same time as Bradley-Terry model was proposed, there was also other models that people were proposing. Looks like 1950s was a very active time for preference learning. So I'd like to introduce this model called ideal point model, which we will be developing our methods based on. So this comes from the psychology literature. And what Coombs does is the following. So Coombs' ideal point model brings in geometry into the picture. So let's say we have a bunch of alternates that are being compared. And these alternates have some representation in some known space, denoted here by script X. So think of this as a representation space that is semantically meaningful. So things that are similar to each other are nearby, things that the alternates that are different from each other are far away from each other, and so on. The key idea that Coombs has in this setup is to say we will model the user as also a point in the same space. So it's a latent point in the same space as these alternates are being represented. And how much this user prefers different alternates is going to be inversely proportional to how far away the different alternates are from this user preference point. So now if you take two alternates and ask, do you prefer like tomato over pear? If the distance between the representation of tomato is closer to the user's preference point than pear, they would prefer tomato. They would prefer pear otherwise, right? We can also put a probabilistic model on it and say the probability that the tomato is preferred over pear is given by this, where h here is a link function. It has to satisfy certain properties for it to give you meaningful probabilities. But this is a function of the difference of the distances of the two alternates from the user's preference point. So sigmoid is one such link function, but you can have any link function that satisfies certain properties mainly that when the distances are equal, you want the probability to be half because there is no clear winner. And when one of the alternate is closer than the other, you want the probability with which the one closer being picked to be strictly bigger than half, which means that there needs to be some signal when there is a clear choice of one over the other. So as long as the underlying link function satisfies this assumption, you'd be able to kind of try to learn either how to predict preferences for this user. So I'm going to pause here and see if there is any questions about this ideal point model. Yeah.
So does it matter which distance function you're using?
That's an excellent question. I'll come to that later. So because one of the key things that we will be looking at is how do you also learn that distance function? That's a good question. Any other questions? Yeah. Because this is kind of thought of as the ideal item in this space. So if there was an actually item exactly at U, that would be by definition in this model the most preferred item. So that's why it's called the ideal point model, because the user preference is thought as like an ideal point. Yeah. Any other questions? Yeah.
Is the choice always between two objects, or could it be more?
That's a great question. In fact, you could extend this, just like in the Bradley-Terry being a pairwise comparison, and then there is the packet-loose model that you can extend to lists. You could similarly extend this modeling to lists as well. But in today's talk, I'll be focusing mainly on pairwise comparison model.
So you decompose the space into Voronoi cells, basically?
Yeah, so that's an excellent kind of observation. So there is a series of work where people have analyzed how many pairwise comparisons would you need to do the ranking of, let's say, given M items, or how do you localize the user preference point using a bunch of comparisons. And the way they would work is kind of connecting back to your question is that you assume you know the distance function. And then let's say take the Euclidean distance, right? So if I'm comparing item I and item J, I can look at the hyperplane that is in the midpoint of the two items. And if I ask you whether you prefer I or J, and if you tell me you prefer I, then I know that your user preference point is to the side of I of the, and so yes, so most of these algorithms and kind of rely on that geometry and to provide like sample complexity analysis. Yeah. The other thing I want to highlight is that if you assume H to be sigmoid, this would be equivalent to a Bradley-Terry model with specifically the reward function being modeled as this distance function with this unknown latent variable. The other thing that I want to highlight is that when you are able to exploit the geometry, the nice thing about this model is that it allows you to, dramatically decrease the overall number of arrangements of the items. So if you have M items, there is M factorial possible arrangements. But when there is a geometry dictating the preferences, now you go, if it is in dimension D, then instead of having N factorial, which grows like M to the power M, if you are in a D-dimensional space with M items and you count how many Voronoi cells there would be among all possible pairwise comparisons, you'll realize that it was going to be of the order M to the power D. So that allows, so that in the literature, when people were looking at sample complexity, essentially what allows you to go from M log M, where M is the number of alternates being compared in ranking, to D log M. So this was like for example, work by Jamieson and Nowak in 2011 shows how you could do active querying to do ranking and so on. Now, if you look at past works, there are a couple of limitations. One is most of these models, like the understanding in terms of like algorithms and so on, was very much focused on learning a universal model, like learning a single preference point that would on average minimize the loss or errors. And also all the algorithms mainly assume that you know the metric under which you're measuring these distances in the space. However, in practice, people have heterogeneous preferences. And also in most of the modern applications, while if you think about where the representations of the alternates are coming from, we could use the penultimate layer representations from pre-trained models as like the representations for the alternates are being compared. However, assuming that Euclidean distance or angle in that space would capture the way humans think about things being similar and dissimilar could be quite a strong assumption. So often, metric is not known a priori. When we are like interested in even learning the preferences. So here is like the question to kind of to begin with, to overcome these limitations. If we think about, okay, there is homogeneity that was focused on, it's very natural to see how we would bring in heterogeneity in this case, because okay, you have a latent point capturing the ideal preference point. Now, instead of trying to learn a single point, I'm going to just assume that if I have n users, each user have their own preference point. And so that, so if I have n users, I have u1 through uk, that un that are unknown, that are each person has their own preference point. So in the same space, you could have different preferences depending on where your ideal point lies. And instead of assuming that the probability of the preferences over the alternates for given a user k now is a difference of distances between the user specifically instead of a single you're conditioning now on user k. If you queried user k, you look at the difference of distances of the alternates from that specific user's preference point. And instead of assuming I know the distance function, what we're going to do is to say that there is an unknown mapping that takes the items to some other space. And in that mapped space, I'm going to use Euclidean distance or angles as my distance function. So I want to learn both the unknown mapping f and the unknown preference points for the users from the pairwise comparison data. Yeah. Yeah.
Model. So there could be a case that this way of putting u in the same space as x would not perfectly match my order. Suppose these are the 4 points.
Yeah.
Four types of fruits that I really like. And right in the center of the square is a fruit that I hate. Where would you put me in that space?
Yeah.
Because like,
Yeah.
I don't know who put these x's in the space, right? It's
Yeah.
a unique way of putting, like, but maybe for me, and there's no combination of these ordering. There's no u that would satisfy
Yeah.
the condition for me, right?
Yeah, I mean, that's an excellent point. So here, like the assumption of like this representation space is that it is like a semantically meaningful space where items that are similar to each other are near, and items that are far away from each other are yeah. So that's the distance function, right? Like so essentially the assumption that's going in here is that there is a shared sense of things being similar, like whether an apple is closer to a pear or a carrot, there is a shared sense of like the similarity between those. But whether I like apple more or carrot more could be different for different people. So the assumption in ideal point model is that that geometry is a meaningful geometry. If that assumption doesn't hold for the preferences, then this wouldn't be a good model. Yeah.
I mean, isn't it just that this is the probability? And so you have a low, you have a low probability outcome for what like you have this weird preference, right? And so, but this is not a deterministic thing, right? This is a probabilistic thing. So there is some probability that you will get a bad outcome. This is fact.
No, but it's gonna violate some of the rules, right? The rule is like if I'm closer to somebody.
Then the probability is high, but it's not.
But if
Exactly.
if I like these 4, but the middle one is the one that I hate, where would you put me?
No,
Where would you put me?
because like, isn't it that the 5 fruits are placed that way because a lot of the population likes them differently from you,
Sure, yeah.
and hence you are an
Exactly.
outlier user,
Yes.
and hence this probability will be low for you.
Not only that, but also like, I think like the concern, if I understand correctly, Aryan's concern is that the probability of you picking the one that is closer to your preference point should be more than the other. So he's asking, what if there is a setting where there are 2 alternates where one is closer than the other, but I prefer the one farther away. But in this case, like, it's actually, here it is modeled as noise and not a systematic thing. But there could be applications where that might be the case. but that wouldn't be covered in this one. The other thing I also want to highlight here is that, so what you are asking is like, is the difference between I was commenting on like the m factorial possible arrangements
Right.
versus now you can only do order m to the power d
Right.
because of the geometry. And it's one of those things where like pros and cons. The pros is if your geometry is a good model, then you will dramatically reduce your sample complexity. But if it is not a good model, then you would be like not doing a good job of predicting.
If you're learning a feature space, I'm cool with that. My concern was the feature space is given, these X's are given.
Yes, but I'm learning the mapping though. Now I'm learning a new mapping on those.
With the feature space.
Yeah.
Then there is no way that your preference is consistent
Yes.
with the locations of X.
I agree, but in this one, we were not concerned with that because that would be the question of like, whether can you put things on a metric space? If you can't put things on a metric space, none of this would good work. Yes, yes, yeah.
So even if you have a well-defined metric space, right, that's meaningful, for example, x-axis is how many hours per week I work, y-axis is how much I earn. Right? There's no ideal point because how much I earn, I want to be at infinity, right? So I always want to be higher, so I can't really place a point.
But there, your preference is not going to be just a function of how much you earn. You will also care about how much you're working because we don't want to like, we can't work all the time. We need to rest. So then your preference is, no, your preference now is in 2D. You're a function of like both how much you work versus how much there is a trade-off there and your preference would be a function of both.
No, that's true.
Yeah.
I think the ideal point, right, assuming crazy, right, would be 0, infinity.
That's where, I mean, we can take it offline, but I would say no, because I would consider both dimension of time and payment. And my preference point would be one coordinate would be payment, the other coordinate would be time. The infinity of the payment will make me put in also in infinite, like, or like all the 24 hours working, which I not want to do. So, yeah.
I think we started late.
Yeah, so I think
We
I,
have like in
yeah.
theory 15 minutes more, so you might want to like.
Yeah, so, okay, so for the theory purposes, I'm going to analyze this mapping being a fully connected linear layer. But in practice, we do learn neural networks for real applications. So if we ask this question of okay, I want to learn now, simultaneously learn the metric or this mapping as well as user preferences from pairwise comparison data. So how much data would I need in order to be able to learn these in a way where I can predict new preferences well? So you can set this problem up as usual through like our empirical risk minimization framework. Write down your favorite loss function. You could use like hinge loss, logistic loss. And so you write down your empirical risks. Here y represents +1 if for the pair ij, if like I was preferred over j for user k, and this is just looking at the difference of distances. And my variables now are the metric, or here M is the Mahabalon's metric. So it's a semi-definite matrix, positive semi-definite matrix. And some constraints, and these constraints are essentially saying that you can't have unbounded metric, you can't have unbounded user preference points and so on. Things have to be bounded if I want to be able to meaningfully learn it. And if if you have a reason to believe there exists some low rank structure in your metric, you could also impose constraints that would encourage that and so on. And if you do, and if you look at, okay, what is the excess risk between the learned metric and the user preference points and the optimal metric and the user preference point, up to log term, it scales in this way. So here the denominator is the total number of pairwise comparisons. And now when we look at and do a sanity check of what is the degrees of freedom that exists in this problem, if you had a full rank metric M, you have order D square entries for the metric, and you have capital N users. They all have user preference points that could be arbitrarily different, lying in D-dimensional space. So you need N times D for that. So roughly what this means is that if I have at least order D people, then with order D queries per person, I can learn both the metric that is shared across people and also different user preference point for different people. And the nice thing about this is that even if I knew the metric a priori, I still need order D queries per person to be able to learn the preferences for each person. So there is like an amortizing of the cost of learning the metric that is shared while learning individual preference points. The other thing I want to highlight is there is more details in the paper of like if you had like a low rank structure, then instead of D square, you can have like R times D, where R is the rank and so on. Now it's a very natural to wonder, like, do I really need order D queries per person? To investigate this, we kind of, because think of like, let's say taking representation from like clip, for example, right? You have like close to 1,000 dimensional space. Do I really need to be making like 1,000 queries per person in order to be able to do this? If we ask ourselves, what if I want to just learn the unknown metric and I didn't necessarily care about learning individual preference points, is there even hope of doing that without making order D queries per person?
I'm sorry, I have a question. So what this means is you want to embed the X's, but you don't want to embed the U.
Yes, yeah. So if I cared only about the learning the function f, the embedding function f, but not the user preference points, is that at least possible with like little o of D queries? What we show is that that in general, no, in the sense that if there is no low dimensional structure that you can kind of exploit, and we have a technical definition of what we mean by this generic pairwise relation, but intuitively what it means is that there is no low dimensional structure in the problem, then what we show is that doesn't matter how many people you have, if you have less than D queries per person, then you won't be able to learn anything about the metric. So it kind of tells us that we do inherently need to exploit some structure if we want to hope for anything better than order D. Yeah.
In here, the recovery is for the metric or the risk with that metric.
So the guarantees that I showed is generalization guarantees in terms of excess risk. In order to talk about the metric, in the paper, we do have guarantees for the metric, it's and the user preference points. But there you would need to assume something about the underlying link function because you have to now believe the model and then say, did I recover my metric correctly?
So the impossibilities for recovering.
So this one is actually to recover the metric.
What if I just impose that I just want the risk to be small? I don't care, but if I.
Yeah, but like here, what we show is that you can fit I can fit any metric, and it will all be fitting with the data. So you won't know, like there will be no way to distinguish one from the other. Yeah, I can talk about this more, like, yeah. So there are two different kinds of structures. I think with the interest of time, I will probably take the questions like in the end, because I do want to make sure I can go to the next part of the talk. So either we'll have to exploit some kind of structure in the alternates we are comparing, or we will have to exploit structure like perhaps in the user preferences themselves. What I mean by points we are comparing is that, if you're in a setup where you have like, alternates lie in, like, let's say similar types of alternate lie in like low dimensional spaces, then you could learn the metric that is just on those subspaces first and try to kind of stitch the metric together as long as some certain conditions hold. But what I want to focus on the rest of the talk is how do we exploit structure within the user preferences themselves, right? So we have like this personalized reward function, that's kind of captured by this latent UI for each I. But even though all of us in this room might have different preferences, perhaps there is some commonalities as well in those preferences. And so what we're going to do is in order to exploit that structure, we will bring in mixture modeling approach towards learning the user preferences. So to be more precise, now what we assume is that, okay, the reward function here for user I is the is this distance between the ideal point in the mapped space to the alternate in the mapped space. But this idle point AI, denoted now as AI, is a convex combination of k prototypical ideal points. So now we have this mapping F and the prototypes that are shared across the population, whereas the weights are different for different people. That allows you to still have individualized or personalized reward functions that you can write down. And so in other words, if I could put everybody's ideal preference points in as a matrix, we are assuming that that can factorize into a matrix of just the prototypes and the matrix of weights. And now the question is, okay, I want to learn like, F and the prototypes, leveraging everyone's data, and the weights are going to be learned only using the specific user's data. I also want to highlight there are two types of generalization that we actually care about. The first is the kind that we already talked about, where you have a bunch of users in your data set and you have some pairwise comparison that is made per user, and you want to be able to learn how you would predict preferences for these users, but for pairs that were not compared. So we call it scene user generalization or scene accuracy. But in general, in applications, we also care about a completely new user who is not in the data set. And for such users, what we can do is to keep the mapping F and the prototype that is learned fixed, and do like a few short learning for just learning the weights, and then start personalizing to the new user. And I'll call unseen user accuracy for this new user. And on the theoretical side, if we look at, okay, what happens to the sample complexity when we bring in this new structure for user preferences, now you have this empirical risk minimization along with our previous constraints. You're going to add like this extra constraint of like how the user preference points are being modeled as this convex combination of prototypical points. And if we were to do that for seen user generalization, that means predicting new preferences, but for people who were in the data set. Now the excess risk is bounded as follows. So as usual, like from before, capital S here denotes the total number of pairwise comparisons. And now if we look at the numerator, we see that previously we had d square plus d times n. Now we instead have k times d and k times n, and that kind of makes sense if we think about the degrees of freedom now in our problem, that the metric still needs d square, but I have k prototypes in d dimensions, and each person has a weight vector of length only k now. So if we have sufficiently large number of users, what this means is now instead of requiring order d queries per person, we can get away by order k queries per person, because we are leveraging this additional structure that we have modeled. Now, what happens for the new user is, as long as this user is a typical user compared to the data set that we collected, we are going to fix the m hat and the user preference points, the prototypes that were learned, and only learn the weight for the new user. And so now the excess risk is like slightly kind of a little bit more complex to think about, because the m hat and v hat were learned on some other data set, right? So when we think about the excess risk for a new user, it's going to have two terms. The first term you should think of it as being small if we have done a good job of learning the m hat and the prototypes on the data set, because there's no way to kind of somehow magically do well for a new user if I couldn't do well for the people in the data set in the first place. So the first term is just capturing how good is m hat and v hat. The second term is what's telling us how many samples, little m is the number of samples for the new user. And what we say is that with order k queries for the new user, we can now also personalize to the new user. I'll skip the simulation results in the interest of time. The main thing that I want to highlight with these results is that you don't need to know the number of prototypes a priori. What you can do is just treat it as a hyperparameter and do cross-validation and start fitting with k equal to 1, 2, and c, and what happens is at some point you'll see that you're not making any more, you're not adding any more value by increasing the number of prototypes. And so that will give you a sweet spot. Now, before going to the real experiments, I want to introduce a slight modification to the model. So we were thinking of this ideal preference point so far. In many of these applications, like for example, the text to image generation model that initially I motivated with, it's more natural to kind of think of ideal mappings instead of like ideal point. So what do I mean by that? Let's say that I have a prompt image of a cat, right? And there is like two outputs that are produced by the model, and then they get mapped to some space. And the prompt is also being mapped to the same space. But maybe the space where the prompt gets mapped to one person is different than it would get mapped to the other person. So the same prompt of image of a cat, what I have in my mind could be different than what Aryan has in his mind, right? Like, so now, the green user would prefer output 1 versus blue user would prefer output 2, right? And on top of it, we essentially now do the similar kind of mixture modeling approach. So now the reward function is the angle between where the output is getting mapped, which is modeled as common for everyone, and where the prompt is getting mapped, which is personalized. And this mapping, we further assume a mixture modeling on top of it, which means that this mapping is a convex combination of k prototypical mappings. So now the goal is to learn the mapping F as well as the prototypical mappings that is shared across everyone, and the weights are still different for different people. And so it's still giving you a personalized mapping. And similarly as before, we care about both seen and unseen user accuracy. And for a new user, you keep your F and G fixed and only learn the weights. So let me show a couple of experiments. The first experiments are on text to image setup. So this is a data set called pick-a-pick data set. A large number of like prompts and pairwise comparison of the output. So when we were running these experiments, the state of the art was pick score proposed in the paper that also looked at the pick-a-pick data set. And what they were doing is essentially fine-tune the last 20 layers of clip to get the on the data set to get around like 71%, 71 to 72% accuracy. So what we were able to achieve is essentially around the same accuracy, but with 100 times fewer parameters. So what we did is to not touch the clip at all, just take the representation from the penultimate layer from clip, and we learn like a 2-layer MLP for on top of it for the for our F's and G's. And so when we looked at the parameter efficiency, we were able to get state-of-the-art results with much less parameters. But more than that, I think there's also an advantage for not really touching the foundation model. And that we could see when we looked at, so pick-a-pick dataset has version 1 and version 2. So if you look at what happens when you train the model on the reward model on version 1, and you try to predict on the test set of version 2, what we noticed is that pick score here, it kind of reduces, it's like from 71, it drops to 68. So there's quite a bit of a drop in the performance for pick score, whereas PAL model keeps its performance pretty similar. And this, I think it's essentially because we don't really touch the clip model at all. And our reward function is a very simple 2-layer MLPs. And it's able to actually, generalize better when you have a slightly different version of the data set. So that was the example for text to image generation. The modeling is general. I'll take questions after I finish showing these other experimental results. the modeling framework is very general, so you can apply it to different types of application domains. So the example I just showed was text to image generation. Now I'm showing text to text, like using like language model generation setup. So this is a summary data set where you have like a Reddit posts that have been summarized. And there is here it's a semi-real data set, in the sense you've created two groups of people where one likes shorter summaries, the other likes longer summaries. So when we looked at the state of the art at the time and compared to our approach, we were actually able to get slightly better performance from the state of the art, but again using way fewer parameters than before. And note that in our setup, like there is these choices of the underlying foundation model that you can also make, like where the first set of representations come from. And in language models, there is no need to actually use necessarily the same model for generation and the model that you use for representations when you are learning these preferences. And in fact, there can be more benefits of using encoder versus decoder model for one versus the other. And my students did an extensive experiments of looking at what is the test accuracy that you can get. So the test accuracy on the y-axis and the different number of like learnable parameters on the x-axis. And here is the orange point is the previous state of the art. And not only could we get this opt 320 here is the number shown here, but if you switch to slightly larger models, you can actually also get better performance. But here we were also slightly fine-tuning the language model. So what we wanted to do is, that's why we call that the PAL-B large. But we further looked at switching out some of these models to other types of models. In particular, if you switch out these models to distill BERT, you can actually, again, like keep your the parameters are much smaller here, but the initial representations that come from this are much better for the semantically meaningful kind of underlying representation you're looking for. So in fact, you can even get essentially the same benefit as these much larger language models when you use representation coming from distilled BERT. But more encouragingly, if you keep distilled BERT fixed, but you are only going to learn fixed two-layer MLPs, you can get nearly as good performance as these, as like fine-tuning the models themselves more. So here you can actually get pretty good performance with keep your underlying language models fixed, only 10 two-layer MLPs for your reward function. So the takeaway there is that if you're using good foundation models, you can actually get away with pretty small reward functions to capture preferences, at least in the data sets that we have tried so far. And you can also see the seen versus unseen user generalization. For unseen user generalization, you can here is the seen user generalization numbers, and you can get pretty similar results with new users, even with like few, this is like around 10 points per new user, and you can get pretty much the same performance as seen users. And there is more experiments we did with like creating different personas and trying to see how I told you about, like, you could do kind of cross validation to get the without knowing the K a priori. And that seems to work pretty well, even like when you experiment more with language models. To wrap up, so the advantage of this modeling approach is that it is sample efficient because we are leveraging a lot of structure and commonality across the population. The modular design allows you to kind of really adapt to new users while like sharing the cost of learning all the common parts of the model. The nice thing about being like starting with writing a model that's agnostic to very specific application is that we have this mathematical model that we could now apply to a wide variety of different application domains. Allows for few short generalization to new users, and so far what we observe is essentially with 20x to 100x fewer parameters we can get state-of-the-art results. to end, I want to highlight a few open directions and also some of the limitations with the current data sets. One thing we noticed is that a lot of the data sets are collected without thinking about heterogeneity. So most of them are collected with a rubric. So when we teach large classes, we usually have multiple TAs and we create a rubric so that there is uniformity in grading, right? So when there is a very strict rubric on how to do preferences, so rubric is different than giving instruction on how to do the task. So when we do rubric, that means that I am crowdsourcing my preferences to get the just to the crowd. So if you really want to if you are looking at a problem where you really care about the preferences itself of the people, then we need to be very careful about how the instruction is provided. So enough instruction to do the task well, but not kind of homogenizing the preferences themselves. So there's a lot of interesting questions about like requiring data sets and benchmarks. But also the other thing is because there is also highly imbalanced, where there's a few people providing lots and lots of pairwise comparison and most people providing like too little. In that kind of scenario, what happens is we can only end up learning a model that fits like those 4 or 5 people that have given lots of data. So you do need enough data per person to be able to capture the heterogeneity across the population. Some of the open directions in terms of reward modeling itself, like we were looking at a very specific way of reward modeling where we are looking at these reward functions, like taking this kind of a specific form. But you could also consider general functions for, you can kind of rewrite our model in a way where the reward function is written as a convex combination of a bunch of k prototypical reward functions. So instead of using a very specific structure, you could also learn certain function classes as the prototypical reward functions. And I just mentioned the data sets and benchmarks. And the other direction we are currently also looking at is how do you adapt these on the fly? Because everything I talked about today is in the passive setup where you just take the data, you learn your the prototypes and the metric, and the only adapting is for a new user to just learn the weights. But you can also be in scenarios where you see new users, where you see that like maybe the Ws we are learning is not still like doing a good job of predicting preferences for them, which is a good signal to say that, hey, maybe the number of prototypes I have is not enough to capture this new type of people that we are seeing. So you can adapt these models on the fly. And any question that is related to the usual learning problems also actually falls here, because many of these data sets that when we evaluate, the kind of like prompts being used, those generalizing across users, but also across like prompts. So we'll need to pay attention to OOD generalization across prompts. And finally, I think we should think about personalization in conjunction also with global safety constraints. So there's some kind of like global safety constraint that the system has, and we don't want the personalization being able to break in order to do well for the individuals, we can't break the global safety constraints. So with that, thank you all for your attention. And